My name's Chris. I'm talking about hunting for alien worlds. So these are planets around other stars, also call them extrasolar planets or exoplanets. And the tack that I've kind of done here is just to kind of pin on the underlying physics that we actually use to go and hunt for alien planets, and what we can learn with that underlying physics. And that's something that you can put into the school setting, because it is actually quite simple. The process is complex, but the underlying physics is quite simple. So I want to go out, I want to find a planet. Now, if I go outside, you might think, okay, when did we first find an exoplanet? We first find a planet around another star like our sun in 1995. And that got the Nobel Prize a couple of years ago. And you might say, well, why did it take so long? Okay, why kind of 1995? I can go out there, and I can see planets. Well, it's cloudy tonight, but if I could go out, I could see Jupiter. And the reason is that it's fairly easy when you're in the actual planetary system. But the problem is we're looking at stars that might be tens, if not hundreds of light years away. So we can't just go out to a telescope, take a picture, take an image and go, oh, there's a planet. There's only very few circumstances that we can actually do that. If I'm an alien and I was looking back at our own solar system, Jupiter, which is the biggest planet in our solar system, would be about 300 million times fainter than the sun. And because it's so far away, basically it just gets lost in the glare. So we have to basically pin on indirect methods and other bits of physics to infer the presence of a planet. We very rarely are able to see the planet itself. So the bit of physics that we look at here, this is not to scale, but this is showing a planet orbiting a star, except it's not orbiting the star. This is the star here. It's not orbiting the star. The star and planet are orbiting the center of mass of the system. So it's just like this kind of lever weighing scale, if you like. So in this case, this is my heavy mass. It's closer to the center of mass on this ruler. This is my planet. This is the smaller mass that I have. I don't see my smaller mass. I don't see the planet. But if I give that ruler a spin, I'll see the big mass jiggling around. Okay, so that will be spinning around, which is exactly what I'm seeing here. And this is actually one of the things, bits of physics that we actually use. The problem being is, again, I don't physically see my star wobbling around as the planet orbits around it. I don't see that. So I need another bit of physics. And I don't think I need to talk too much about the picture on the left, other than that if you're daft enough to stand in front of a train while it's coming towards you, you're going to have the sound waves bunch up. So you'll hear a higher pitch. If you're a little bit clever and you're behind the train, you'll see them stretch out, the Doppler effect. That's actually what we use to infer the presence of a planet, except we're not looking at sound, we're splitting the light up into its constituent colors. Okay, so we've got a nice rainbow, and what we see is as the star is shifted towards us, we see the colors. It's not quite as simple as this, but the colors kind of blue shift, and then as it moves away from us, it becomes red shifted. Okay, and it's that we actually track when we're trying to find these planets. How do we actually go about doing this? You've seen a few pictures. Meg showed a picture of a particularly big telescope in Chile. This is another set of telescopes in Chile. Up here, you might see the mountain in the distance. You can see this road going all the way down here. This is a set of very large telescopes. There's another telescope out here, and down here you'll see the actual area where the astronomers actually stay. Predominantly engineers, actually. There might be a few hundred engineers supporting this. Last time I was there, I was actually the only astronomer there. This is part of the building, what we call the residencia. In this part of the Atacama Desert, there's just nothing there. There's not even life. It's really, really dry. Some people might recognize this building. Some people might not, but James Bond blew it up not so long ago. So we're looking at big bits of kit that we actually need to make this work. So again, this is a very large telescope. This is just one of many observatories that can be used for this work. Within here, there's a picture of the telescope. There's a 8-meter diameter mirror. If we give you a bit of scale, you might just be able to see this chap here. And then there's actually, if I'm down here, there's an engineer on the ground, just to give you a scale of the kind of kit that we're actually using here. And it's these big light collecting buckets that we then go off. We take a spectrum of our star. So this is just a bit like that rainbow that I showed you earlier, but you'll notice just above my laser pointer, there's kind of these black cuts, if you like, in the spectrum. We call these absorption lines, and these are things such as iron, aluminium, calcium, magnesium up in the upper atmosphere. You know, we think of it as metal here on Earth, but essentially it's vaporized in the sun, and they're actually absorbing light from the sun. And we see this nice kind of DNA fingerprint sequence of these absorption lines. And it's actually these absorption lines that we monitor shifting back and forward. So rather than listening to a pitching sound, we're actually seeing the kind of reflex motion induced by an orbiting planet, in the sense of these lines periodically moving back and forward. What do we get? That gives us an indication of the mass of the planet, because I know the mass of the star. We're very good at estimating that. By looking at a star, we can determine its mass and radius fairly accurately, and how much it wobbles tells us where the other weight is, and we can measure the period of that other weight as well. So we get the year, if you like, of that orbiting planet, and we can also get an estimate of its mass. You've seen this kind of pictures in the news. It's an artist's impression. This is not what an astronomer sees. This is what an astronomer sees on the right. This is this Doppler shifting effect. This is essentially velocity. This is time in days in this case. And what we actually see is we see the star moving towards us, and then away from us, and then towards us in that lovely sine wave. We've got a circular orbit. In this case, this is 51 Peg, which was the first planet that was exosolar planet discovered around a normal star. And this is a big gas giant planet, but on a 4-day orbit. It's got a year that only lasts 4 days. So an entirely new breed of type of planet that we call a hot Jupiter. Obviously, there isn't one of like that in our own solar system. So it gives this fundamental physics you can then go out and use and find a whole new class of planet. Another thing that can easily be distilled into classroom setting is looking for something called a transiting planet. So if the planet orbit is just in the right place, then once in orbit, you actually see the planet moving across the face of the star. Now, we don't see this. Basically, the star remains just a pinpoint of light because it's so far away. But what we see is once per orbit, we see the light from that star dip, and Meg and partly myself, you may have heard in the news, set up a citizen science project where we're getting people to actually go and identify these dips in light. If I'm an alien, I'm looking back at the sun and I happen to see Jupiter pass in front of the sun, I see about a 1% dip in the light. Once every 12 years, roughly. For Earth, I would see a 0.01% dip in light. This is why we need to stick stuff into space to get above the blurring effects of the atmosphere. And we would see that occur, repeat once every year, which is quite difficult to do. In terms of how you can transport that into a classroom setting, well, here it is. Here's my star. Here's my planet. Let's make it simpler. That's basically 2 circles. My star has an area pi r star squared. My planet on the sky has an area pi rp squared. And the amount of flux, that dip in light I was talking about earlier, is just basically how much area of the star, which is covered up by the planet, is blocked from the total portion of the star. The pi's cancel, you know this. You know, we're very good at our physics, so we know when we look at a star roughly what its radius is, and that means I can also determine the planetary radius as well. Very, very kind of simple underlying physics on this. So you can get the mass, you can get the radius of the planet, and that's really cool. If you know the radius, you know the volume of the planet, and then you can work out what its density is. And that's the really cool thing that you can do, because you can tell whether I've got something that's big and fluffy, which might be, for example, Jupiter-like planet with a gassy, very light, fluffy atmosphere, or whether you've got something that's really dense with a density that's more akin to rock. So you can then say, oh, okay, this is the kind of planet that is a gassy planet. Probably we don't have life. Here we've got a nice planet that looks as though it might be predominantly rock, and therefore may actually be a platform where you can have life. And I just wanted to kind of feed in very, very quickly some of the discoveries that you've got that are all based on these really fundamental kind of physics and maths that you can have in the classroom. So you can go off and you can measure the orbital period of these things very easily, just how often you see a transit, or how often you see one orbit complete. So we see these big kind of gas giant planets, but they have years that are less than 1 day here on Earth, 21 hours. We can actually also work out in what direction these planets are orbiting the star. So all the planets in our solar system orbit in the same direction, and the sun spins in the same way. We see planets orbiting over the poles. We see planets orbiting back to front. And that's indicating that probably something quite violent happened to toss them into these really, really strange orbits. We also have systems like this. This is Kepler-16. This is just a kind of animation. But here we have, an actual fact, a planet that is orbiting 2 stars, which in turn are orbiting each other. So this is a binary system. So we get these weird and wonderful worlds. So this was called Tatooine when it was actually found. For those of you that can remember the original Star Wars series, here is I can't remember his name now. Luke Skywalker. I think he's had a bit of a bad day at this point. With you know, if you were on that planet, you would see 2 stars up in the sky, and imagine the shadows that you would have. You could think about what shadows we'll have. You'll have one shadow for one star, that would be one color. You'd have a shadow from another star, that'd be another color, and then you'd have another shadow where those 2 shadows overlapped. So you would have kind of weird and wonderful effects that you can imagine on these planets. This is what got me on BBC Horizon. There's a few snapshots where we measured at that time. We were able to measure the mass of the smallest radius planet. It was Kepler-78b, which is here. It had a radius not much bigger than the Earth. We were able to measure its mass. We had the mass, we had the radius, we got the density. It was rocky, smallest rocky planet ever found at that point. What was weird about it, its year lasts about just over 8 hours. So it manages to lap the star once every 8 hours. In fact, if the star is about that size, the planet would be about here. It's so close that in actual fact, when we worked out the temperature of this thing, all the rock that you had would be above about 2000 degrees centigrade. So in other words, we had this lava world kind of story that was going on. So you get all of these really exciting planetary systems. I've got a couple others. I don't know if I've got time, but I might be able to show you a couple more. Andrew, stop me if you think.
Yeah, if you go for another 2 minutes, Chris, then I'll leave 10 minutes for questions.
That will be brilliant. Okay, so just another couple of examples. And again, you can go off, you can get the data for these things if you wanted, and try and get the radii. So again, to show the different types of planetary systems that you have out there. This is a system called Kepler-42. So it was referred to as a tiny solar system. So you have types of stars that are have very small radii, not much bigger than Jupiter. So this is Jupiter and the 4 Galilean satellites that you have. And this was Kepler-42, which is a small, cool, what we call red dwarf star with 3 planets orbiting it, at least 3 planets. And you can basically fit this entire planetary system inside the Jupiter and the Galilean satellites within our own solar system. So we see all these kind of crazy and weird and wonderful systems. There are other things that you can do. So this is going to be my final, second last slide, just again to enthuse you on what you can dig out with quite simple physics. So here's an example of a transit. Okay, so I've got something that's fairly flat, and then something passes in front of my star, and I see that kind of dip. Okay, so this dip is a little bit less than 1%. Okay. When I observe it a little bit later, the dip is smaller, okay? I don't have such a big dip. So you can go off and you can actually work out, well, okay, what's the radius in both cases? And you're left with this kind of problem going like, well, how on earth, if this is a planet, how on earth has the planet changed size between two different transit events? Well, it hasn't. There's something a lot weirder going on. And what we actually think is going on in this case is we actually have a small planet. So this thing repeats every 15 and a half hours. What we actually think, and hopefully you can see this, is we have a very small planet, probably the size of Mercury. We can't see it. But because of the short orbital period, it's been ripped apart. And what you're actually seeing is dust, and hopefully you can see this. It almost looks like a comet that's going around the star system. You're seeing dust, and we see the difference in the size of the transits, because when I have a deep transit event here, I'm blocking out more light from the star. That's actually because there's a larger basically cloud of dust that's been evaporated off the surface of this planet. And then at other times we don't see as much dust, as basically this planet is being blasted apart. So there's loads and loads of interesting stuff. You can go out there and you can actually get this data and you can find planets, and we do not have these types of planets in our own solar system.